find, d plus g nabla f and d minus g nabla f. So this was the limit as epsilon going to 0 from above and this from below of the same quantity, and the quantity is the minimal weak upper gradient of f plus epsilon g squared minus the minimum weak upper gradient of f squared divided by 2 epsilon. And then I also gave a definition. I say that x is infinitesimal Hilbertian. If W12 is Hilbert. And then basically I concluded the lecture by stating a result concerning how this d plus d minus g nabla f reads in the case of infinitesimal Hilbertian spaces, and basically the calculus rules they obey are those of grad f grad g morally. So the theorem, proposition, whatever, tells the following: say x is infinitesimal Hilbertian. Okay, then a few things are true. So first of all, d plus g nabla f is the same as d minus g nabla f. And the map that takes, fg into this, same quantity is bilinear and symmetric. Bilinear, symmetric. And satisfies a few things. So we call it, once you know that this bilinear and symmetric, call it, df dg. Because now it's bilinear symmetric and satisfies, Cauchy-Schwarz. Yeah. I mean, what looks like a Cauchy-Schwarz. Equality if f is equal to g. Of course, this is almost everywhere. Okay. It is local, namely, what is df dg is equal to df prime dg prime m almost everywhere on the set where f is equal to f prime and g is equal to g prime. Satisfies the chain rule. And here, phi is Lipschitz. And just, let me also add the C1 on R. It's not necessary, just Lipschitz is sufficient. But if I drop the C1 assumption, I have to work a little bit more, and I don't want to do this. And then df1 f2 dg is equal to f1 d f2 dg plus f2 d f1 dg. And finally, integration by parts for the Laplacian, if the integral of g Laplacian f dm is equal to minus the integral df dg. Okay. And this, of course, requires more than f living just in the Sobolev space. Of course, f should have a Laplacian in order to make sense to this expression. So let me write this. Okay. Okay. I'll come to the, so perhaps one comment. Okay, one thing that one could say is, okay, W12 is Hilbert, I polarize, and when I polarize, I get a scalar product. End of the proof. So that's. However, this is, there is some polarization going on in this proof, but it is harder than just this. And the problem is that what a priori it's not clear. It will be clear after this, it will be proven, but a priori it is absolutely not clear that if W12 is Hilbert, I don't know a priori whether the map that takes f and returns, say the integral over a certain given set.
Nicola, sorry.
Yes.
The right blackboard.
Yes. Sorry. Yes, I did not notice it. Maybe it's this.
Yeah.
Yes.
Good. Thanks.
So I was saying that W12 is Hilbert tells that this map that takes f and returns the integral of the minimal weak approximation squared over the whole space, that this is a quadratic form. Okay. Now, what is a priori not clear is whether it remains a quadratic form when I integrate only over a certain Borel set. Okay. So whether if you want, whether so being Hilbertian at the global level means implying being Hilbert even at a local level, or if you wish at a pointwise level, as in the statement of the proposition. Okay, in some sense, being Hilbertian is not a variational characterization, so this is not immediately obvious. I'm basically proving this statement is more or less like proving that this is a quadratic form, and this is strictly related to proving the Leibniz formula. Okay, so in fact we will first prove the Leibniz formula and then prove conclude the statement. Okay, the proof of the statement. All right, so it's not really obvious, but it can be done. It's not even that complicated. Let me first observe the following. Okay, so first of all, we know that's by definition, or what we have seen the last lecture, that d minus g is less or equal than d plus g almost everywhere for every f and g, right? That we know. Okay, and we also know that this guy is actually, yeah, is the limit as epsilon goes to 0 of that expression from above and the other from below. Now, if x is infinitesimally Hilbertian, I know that this guy is a quadratic form, right? That's that's my assumption, basically, quadratic, right? In particular, it's smooth, okay? And in particular, I can take the derivatives from the left and from the right at every point, and these derivatives exist, right? So, right, is that clear? So this implies that the if you want, that the limit as epsilon goes to 0 of Chigger energy of f plus epsilon g minus Chigger energy of f divided by 2 by epsilon, sorry, this exists. Make sense? If you want bipolar here, this is the quadratic form, so you can polarize, right? So this limit is okay. Maybe I can give a name to this limit. This is the, I don't know, let's call it this way, FG CH, the scalar product in terms of quadratic form of this. Make sense? Right? But this, but on the other hand, d plus, the integral of this guy in dm, this is equal to the limit as epsilon goes to 0 from above of that expression. Right? And the integral of d minus is the limit as epsilon goes to 0 from below of the same expression. Make sense? Right? Just by definition, right? And some dominant convergence theorem, right? But the dominant convergence, I can bring lim, the limiting epsilon inside and outside the integral easily, so I get this, right? Now these two are the same because this limit exists. Therefore, these integrals are the same. But I had an inequality between the integrands, and this forces equality to be true almost everywhere. Right? So that's the first step. Okay. Let me call this guy, let me call this quantity. Let me give it a name. Let me call it dg nabla f. Okay. I don't want still to use this expression because this is too symmetric. I don't want to make confusion. Okay, I don't want to choose. So as an intermediate step, let me call it this way. Okay. Now notice the following. In G, even before knowing this, the map that takes G and returns, so the map that takes G and returns D plus G nabla F, I claim that this is convex. If you think for a moment, convex in the almost everywhere sense. This is a map that takes Sobolev functions and returns L1 functions. Okay. So why is it convex? Well, because this is the derivative, the right derivative of a convex function, the Gigli energy, right? Or if you want the minimum weak upper gradient to be more precise. And the derivative of a convex function is always convex. Right? Make sense what I'm saying? So if you want, let me be a bit more explicit. So how much is it? D plus 1 minus lambda G1 plus lambda G2. Well, this is the limit as epsilon goes to 0 of what? Differential of f plus epsilon, let me call G lambda just for brevity, squared minus differential of f squared over what is it, 2 epsilon, right? But now for any given epsilon, this expression, is convex in this variable. Make sense? Because there is nothing here, This is a convex function, as we already said, right? So this expression is convex. So you apply the convexity inequality, and you have a convexity inequality for every epsilon that passes to the limit and tells you a convexity inequality at this level. Nabla. Make sense what I'm saying? Right. So this is convex, and of course it's also a positive one homogeneous, and D plus lambda G nabla F is equal to lambda D plus G nabla F for every lambda positive, just by scaling. It's a right. It's a derivative. The derivative is always one homogeneous in the differential variable. Make sense? So this guy is convex and positive one homogeneous. Of course, D minus is concave and one homogeneous for the same reasons. It's concave, and positively one homogeneous. Right? But then D plus is equal to D minus. So the map that takes G and returns dg nabla F, this is both convex and concave, so it's affine, and it is positive one homogeneous and also negative one homogeneous, so this is linear. Okay, so half of this is done in some sense, right? So it's linear in one variable. Right. Now, this is obvious, because if you look at the definition, this is obvious from the analogous property of minimal weak upper gradients. You remember that if f and f prime agree on a certain set, then the minimal weak upper gradients also agree on the same set. Now you write the definition. Okay, perhaps I should say of dg, nabla f is equal to dg prime nabla f prime. I mean, in this sense it is, so on this set. You agree? Just by definition. In fact, also d plus and d minus are local in the very same set. All right. So this is proved. So that's okay in some sense. Let's check Cauchy-Schwarz. Okay, Cauchy-Schwarz is also obvious. So why is that the case? Well, what it is, the let's say d plus g nabla f. I mean, let's have a look. Actually, let's have a look perhaps to that expression. So that's the limit in epsilon of of that difference quotients. So, but let me say then that this is less or equal than the lim. Let me expand the minimum weak upper gradient over there. So that is df plus epsilon dg, right? Squared minus df squared, so squared divided by 2 epsilon. You agree? I should be a little bit careful of what I mean by this lim-inf. One possibility is take any sequence as epsilon goes to 0. And you have a sequence of L1 functions, take the pointwise limit of that sequence. So any sequence, so this is going to be less or equal than any limit you would obtain in this way. Okay. If I don't do this, I should explain what it is the essential lim-inf of a family of functions. Okay. Okay, now you expand. This is equal. I mean, now you expand the, the df disappears. In front of the dg squared, there is still an epsilon. Does not simplify. The only thing that remains of order of the correct order is df dg. And then d minus is bounded from below by the by the same trick. So the Cauchy-Schwarz is obtained. So that's okay. So that's okay. What about this? What if you plug g equal f, you get the differential of f plus epsilon f is the same as the differential of f times 1 plus epsilon, and so you get this, right? Okay. Sorry. Sorry, you say that's something wrong? Yes, that's okay, right? I mean, this.
Sorry, I thought if okay.
No, if f equals if. Okay. Right. No problem. No problem. Okay. Other questions? Yeah, don't feel afraid to ask questions or whatever that's. Okay. Okay, so I've done this, and this. Let me prove the chain rule. Okay. Notice that we already know that if I is Lipschitz C1, and actually, and if G is Sobolev, let me practice it. So I already know that phi composition G is W12 if G is in W12 and phi is C1 and Lipschitz. Right? That we already proved. Okay. So at least this makes sense, right? Because I can, there is a Sobolev quantity over here. Now, if phi is linear, this holds. Because I already proved. Actually, I'm making confusion between f and g. So let's check whether this chain rule holds. Let me write this way. I claim that this is equal to phi prime composition g dg nabla. All right. Now, if phi is linear, I know this, and I know this because by linearity of this guy. If phi is a constant, I also know this because if phi is constant, this is 0. All right. And so I need just to check that the differential of a constant function applied to grad f is 0, but that you can check, the minimum weak aggregate of f plus constant is the same as the minimum weak aggregate of f. Okay, doesn't really change. Okay, so if you are bordered by the fact that adding a constant f that is not anymore in W12, feel free to think that the reference measure is finite. Say m is probability, so I add a constant to a function, it still remains in L2. Okay, this of course is irrelevant. I mean, all these arguments are extremely local in nature, and so the global mass is not really a point. A way to handle this from the technical level is to work with the definition of weak upper gradient given by test plans, where the integrability of f plays no role. And there you see that constant functions are always in this Sobolev class S2 with 0 upper gradient for trivial reasons. Okay. So this is true also if phi is constant, right? So by linearity, it's true if phi is affine. Okay. So by locality, this is also true if phi is piecewise affine, right? If phi is a function, goes like this. So I can divide R in a family of countable family of intervals, and phi in each of these is affine. Okay, as far as is globally Lipschitz, by by locality, this works. Okay. So now I want to pass the limit, and what I want to, what I notice is that so if phi is C1 and Lipschitz, then there exists a sequence phi n of piecewise affine and global and the uniformly Lipschitz functions that is so converging uniformly to phi, and such that phi n prime converges also in some sense uniformly, or at least pointwise, to phi prime, for almost every z, phi prime of z. Okay. Let me say for every z. Okay, for every z except a countable number. Let me go this way, except a countable number. I have to, these are piecewise affine, so on some points they will be not differentiable. Forget about those points. On the rest, they converge, if you want, even uniformly. So what am I doing here? I'm just saying I have a globally C1 ellipsis function. I just divide R uniform in the interval, and then each of these interval, I take the affine interpolation. I pick this sequence. Okay. Okay, now so I know that this is true for every n. This is true, right? Let's check what happens on both sides. So here I have a fixed L1 function, and I multiply it by a function which is almost pointwise converging to phi prime composition. Okay, this goes, in fact, I have pointwise convergence, so this goes to phi prime composition G, except possibly, if you want, on G minus 1 of, countable number, let's call it L, n, okay? Except on G minus 1. On this preimage, I don't know what is happening, right? And this preimage, a priori, this preimage could have positive measure, a priori. But in fact, so there are a couple of ways to handle this problem. So either I prove that on this preimage the differential of G is equal to 0 almost everywhere, and this in fact I know, right? Because on the preimage of any given point, for any, perhaps any point, let me point this out. So so I claim that this is 0 on the preimage of any singlet on Z. For every Z real, this guy is 0. How do I know this? Well, because on this set, G is identically equal to the function constantly equal to Z. And the constant function Z has 0 minimum wake-up agreement. Right? So on this set, this is 0. But if this is 0 on this set, it is 0 on the preimage, almost surely in the preimage of any countable set, just by countable union. Okay. So on this set, where I might not have convergence of differentials of derivatives, this is identically 0. Okay. And for the same reason, the same set, also this left-hand side is identically 0. Because we proved, we know that the differential, we know that the differential, say differential, of course, I mean minimum wake-up gradient. We proved that this is equal to phi prime composition G dg, right? So whenever this is 0, so this is 0. Okay. So on this set where I don't have convergence of derivatives because derivatives do not exist, both sides are 0. Okay. Please.
No, maybe it's stupid, but n is not necessarily countable.
By the way, I chose. Yes, it is. Why is it not?
Oh no, yeah.
It is. So I have piecewise affine function. Each one, it's.
Oh, no, okay.
I'm really doing, the series. I even, if necessary, I also avoid picking intervals that accumulate and then just. So I'm really picking uniform partitions, whatever. Okay. No problem. No problem. So that's so what I'm saying here is that on this set, which is fixed once the chosen sequence has been picked, on this set I have that both sides are 0 almost everywhere for the so in particular I have convergence because they converge to 0. Okay. Okay, so all this proves that this right hand side converges to phi prime composition G dg nabla f, say inner one. This is an L1 function, and I'm multiplying this L1 function by a sequence of uniformly bounded functions. Okay, they are converging almost everywhere. Okay, all right. Okay, perhaps another comment that I want to make. There's another way of handling this issue of non-existence of derivative non-convergence, is that I can arrange a little bit the functions phi n so that this set g minus 1 of n has 0 measure. This I can always do. How do I do? Well, here I have a lot of wiggling room in where to choose these points of non-differentiabilities of the function. Right? It is clear that for almost g1, so the measure of the preimage of a singleton, this is 0 for every z except a countable number. Just because these sets are all Borel disjoint, and you cannot have more than countable sets of positive measure if the total measure is finite or sigma finite. Okay. So if by chance you happen to have chosen a point z where g minus 1 as positive measure, just change a little bit this z. Move it a little bit to find a point with 0 mass, and you're done. Okay. So in either case, I get this convergence. So it remains to prove that this goes in L1 to the differential of phi composition G nabla f, right? But this is true because what's the difference? So what's the difference between, it's by continuity. So basically, what's the difference between, let me write this way, dg nabla f minus dg prime nabla f. Well, by linearity in G, this is d of G minus G prime nabla f. Okay, and now by Cauchy-Schwarz, I mean, that kind of Cauchy-Schwarz. Right? Okay, so I apply this in our case, and what I get is that the difference between phi n composition G nabla f minus this is bounded by the minimum weak upper gate of phi minus phi n composition G df, right? And this is bounded in turn. This is bounded by phi prime minus phi n prime composition G dg df. But now, as before, except on a countable number of z's, where anyway, on whose preimage this is 0, these guys are uniformly bounded and pointwise converge to 0. Okay. But I don't know where this converges to 0. This is 0. So in any case, this guy is converging to 0 almost surely. But this is uniformly bounded. This is in L1, so converges to 0 in L1. So I converge in L1 in here. So I prove the chain rule. Okay. Oh, by the way, the work, let me clarify with this. The work that we do improving this proposition, I mean, even if we knew now this theory of modules that I presented a couple of weeks ago in my talk, the work should still be there. So it's not that, you know, I'm now doing some job that is, in fact, you know, in some sense, becomes old the moment I introduce the concept of actual differential. This kind of proof should still be there. So we are, in some sense, making now some job that we should do anyway, do later on. Okay. So I proved the chain rule. All right. Now Leibniz rule, you know, Leibniz rule is a consequence of chain rule. You know, they don't tell us, but that's what it is. There are various ways of doing this. So one is, I guess, so this is that. Okay. One is to just to what it is. You can, I mean, as soon as you put a nonlinearity, you know, basically any nonlinearity, you're done. So one possibility is to work with the square. The other one is to work with the log. So what is this guy? I have two ways of computing this. Either I first apply the chain rule, or I first expand the square. Let me first apply the chain rule. If I first apply the chain rule to, you know, this is the square of this Sobolev function, g1 plus g2. So by the chain rule, this is twice g1 plus g2, the differential of g1 plus g2, blah, blah. Okay, which of course I continue. This is, well, I don't write what it is. Okay, or I first expand the square, and this is then equal to the differential of what is g1 squared plus g2 squared plus twice g1 g2 applied to Nabla. Okay, now in both cases I use the linearity of the differential, and then let me use the linearity, and then here I still have the term g1 squared and g2 squared, to which I apply the chain rule. Right. So this is equal to twice g1, the differential of g1 applied to grad f, plus twice g2, the differential of g2 applied to grad f, and then plus twice differential of g1 g2 grad f. Right. Now you use the linearity of the differential here. You expand the product, and you get the, you know, this guy and this guy simplifies out, and you remain with the Leibniz rule. Okay. Okay. All right. So it remains, or perhaps I should pay just a little bit of attention. So this should be, so when you apply the Leibniz rule, the function should not only be Sobolev but also bounded. So what I'm using here, so let me perhaps make a comment on this. The square is not a Lipschitz function. So I cannot apply the chain rule with phi equals z squared, because phi is not globally Lipschitz. So what is I do in practice? I do, first of all, I need to work, and for a good reason. I mean, even on RD, the square of a W12 function is not the W12. You have problems of integrability of both the functions and the gradient. So what I actually should have said previously, I forgot, I said it now. G1 and G2 are bounded, okay? And if they are bounded, you know, phi squared is, you know, is Lipschitz on their image. And when you are out of their image, do whatever you want to smoothen them out, and making globally C1 and Lipschitz. All right? Okay. It's now time to prove symmetry, which is, you know, the hardest part in some sense of it. So symmetry comes after I prove two claims. The first claim is that there is symmetry at the integrated level. And the second claim is, well, I guess it's just this. I guess it's just this claim. Okay. Suppose for a moment that we know this. Yeah, suppose that we know this. Then I'm assuming that I already know this. Then what I get is that actually I can prove this easily. There's no need of bothering. So this is true because the Gigli energy is a quadratic form. This is a global statement. Okay. This is on one side. This is equal to what? This is equal to the lim. Let me. I mean, this is actually so. In both cases, let me say. In both cases, then maybe I expand a little bit. But in both cases, this is what previously I indicated in this way. No? This is the scalar product, induced by the global Gigli energy, which is a quadratic form. Okay. Right. So this is true. Make sense? I could expand a little bit more if you want, and notice that. So on one side I have, I guess if you want this. So actually, let me write an identity. The Gigli energy of G plus epsilon F minus Gigli energy of F of G divided by epsilon minus epsilon the Gigli energy of F. This is equal. I'm proving, if you want, I'm reproving with this identity the symmetry of a scalar product induced by a quadratic form. Gigli energy. This is an identity that holds for every F and G. It's basically the parallelogram identity, or a consequence of the parallelogram identity written in this guy's form. Okay. Now, if you believe in this, and you should, I mean, this follows from quadraticity. I mean, it's there's no analysis in here, just algebra basically. When you let epsilon go to 0 in here, you get this. No, you get this. Sorry. Here, this object is basically linear in F, so you get this. And when you get epsilon go to 0 in here, you get that one. Okay. So you have that symmetry. All right. Now, that I have symmetry, let me think for a second if I can do things. All right. If I have symmetry, no, I have to work a little bit. Okay, symmetry, and so another claim is that I have the integrated chain rule. So the integral of differential of G applied to grad phi composition F with the same assumptions on phi. So phi is globally C1 and Lipschitz. This is the integral of phi prime composition F dg grad F. Okay. I cannot deduce this from the symmetry and this rule for the differential, because if I use the symmetry, then I get differential of phi composition. I mean, let me show you. So this, what I know for sure is that, I mean, this is this nabla G, but then for this I know the chain, the chain rule. But then I still don't know that this is equal to this, because I know the quality of these things only when just of their integral. I still don't know the pointwise identity, right? If I knew the pointwise identity, I would have proved bilinearity and symmetry, but I still don't know. So I still have to work a little bit to prove this. But let me show you how the proof completes if I know this. Okay. Now, if you know this, what I would do is the following: is fix, say, a function h, which is, say, Lipschitz unbounded with bounded support, maybe. And let's look at the functional that takes f in W12 and returns the integral of f of h df squared. My dream is proving that this functional is a quadratic form. I know this by assumption if h is identically 1. But I want to prove that this is still a quadratic form for any h. Okay? Which is, I mean, if I do this, that would be the same as, you know, integrating over a certain set by approximation, right? So that would be a localized version of the global quadraticity that I had at the beginning, right? Now, what is this? Well, this is equal to, let me write this way. So this is the differential of h times f, grad f, minus f differential of h grad f. Right? Here I am applying the Leibniz rule. Okay. You can, of course, you know, be annoyed a little bit by the fact that I didn't say anything about f here on the Leibniz rule, which should be in L infinity. So if you want, let's pick f in W12 and L infinity. If you want, it's not really necessary because in this case h is Lipschitz with bounded support. So h times f remains in W12 even if f is in W12. But that's, you know, let me put this integrability assumption f. So by the Leibniz rule, once I drop this out, I get this. Okay. Now, let me rewrite this. Actually, let me rewrite this right-hand side as follows. So by the chain rule, this is equal to, you know, grad f squared over 2 by the chain rule at the level of gradients. And this is equal to, so differential of f squared over 2 nabla h. Okay. Now here's the thing. The map that takes f and returns this expression, this first integral, is bilinear, right? Because sorry, it's a quadratic form, what I meant. So it's linear on this entry and it's linear also on this entry, basically. Right? Why is linear on this entry? By the symmetry and the linearity on G. Make sense what I'm saying? Right? And the map that so this is a quadratic form. Yeah. Right? Because it's linear on both entries in some sense. And what about this? Well, this is also a quadratic form. I mean, there's an f squared, and then after f squared, I do something which is linear in f, because on the left-hand side, this is linear. So this is also a quadratic form. So this is a quadratic form. Make sense? Right? And once it is a quadratic form on the space of Sobolev and bounded functions by truncation, you see that this is a quadratic form on the space of on the whole W12. Right? And if you want, by polarization after this quadratic form, you conclude that the integral of h d f nabla g is equal to the integral of h dg nabla f, right? For every f, g, and h, right? But once you have, you know, these two L1 functions, they agree once you integrate them against any Lipschitz and bounded function. And this forces dg nabla f, the integrals to be the same. Make sense what I'm saying? Right. So this proves at once bilinearity and symmetry. Right? Because once it's symmetric, it was linear in one entry, it becomes linear also in the other one. Okay. Let me now just prove this, and then we come back to our claim. But this is trivial actually, because what is that I should prove? If I pick V, sorry, what was our Laplacian? Our Laplacian was the element of minimal norm in the subdifferential of the Gigli energy, right? So let me pick V in the subdifferential of the Gigli energy F. Okay. And what I wonder is what is the integral, or actually, what is the scalar product of V and epsilon G, this scalar product in L2. And what I know is that, the Cheeger energy of F plus this is less or equal than the Cheeger energy of F plus epsilon G. Right? That's what I know. So for every G and every epsilon, this is true. Right? So what I get is that epsilon Vg, some product in L2, is less or equal than, Cheeger energy F plus epsilon G minus Cheeger energy of F divided by G, by epsilon. No, just this. So I'm really going through, once again, the same proof of the weak integration by parts formula, but now with a better understanding of what this is. Because now, if epsilon is positive, I can divide by this, and then take the limit as epsilon goes to 0. Right? But this is equal, now I know exactly what it is. This is equal to df dg, right? I should have a problem with the sign somewhere. No, that's okay. That's okay. Yes, df. Right. Okay, and then I could then either play with epsilon negative or just notice that, both sides of this inequality are linear in G. And if I have an inequality between two linear things, that this must be an equality. You cannot have one linear function. G, replace G with minus G. That's the easy. Okay. And then when we get this, right? So for any, in fact, for any element, for any element in this subdifferential of the Cheeger energy, what I get is that, V scalar, the integral, if you want, of Vg is equal to the integral of df dg. So this proves in particular that V is unique, right? And that must be exactly minus the Laplacian. Okay. So it only remains to prove this claim. Let me prove this, and then we take a break. This requires just a little bit of work. So first of all, I notice that the map. So notice that the map that takes F and returns D plus G nabla F. So this is actually the integral. This dm. This is equal. So we have already noticed that this is equal to the inf over the positive epsilon of Cheeger energy of F plus epsilon G minus Cheeger energy of F divided by epsilon, right? Now, for any fixed epsilon, this expression is continuous in the Sobolev norm. The Sobolev norm of F plus epsilon G, the Sobolev norm of F. I mean, the gradient part of the Sobolev norm. So this quantity is the inf of a family of continuous functions. So this map is upper semi-continuous. Right. Of course, for the same reason, this guy is lower semi-continuous. Okay. So we know that these two agree, so we conclude that the map that takes F Sobolev and returns the integral of dg nabla F, this is continuous. Okay. And there's one other thing that we know is that I don't know if it is linear. I don't. But I know that it is positive homogeneous. So I claim, or if you want, I claim that dg nabla alpha f, I claim that this is equal to alpha dg nabla f. And why is this the case? Well, I basically observe, this is a consequence of the following identity. The minimal weak upper gradient of alpha f plus epsilon g squared minus the minimal weak upper gradient of alpha f squared divided by 2 epsilon. This is equal. I mean, if you take alpha out in both cases, and you see what this comes out. This is the minimum weak aggregate of f plus epsilon over alpha g squared minus the minimal weak aggregate of f squared divided by twice epsilon over alpha. Just for trivial reasons. Okay? But now when you let epsilon go to 0 here, you get this. If you get epsilon go to here, you get this. So have this, this homogeneity in F. Then, of course, even and much like in dg, if I add a constant, so dg nabla f plus constant is equal to dg nabla f, because for trivial reasons, because adding a constant to f does nothing in terms of minimum weak aggregates. And now I do the same trick as I've done before for proving the chain rule. So what I just proved, if you want, is that dg nabla phi composition f is equal to phi prime composition f dg nabla f for phi which is affine. Okay. Then by locality, this is also true if phi is piecewise affine. Okay. And now I would like to argue by approximation and conclude that this is true, for every phi sig1. But by approximation requires a continuity statement, and I don't have a pointwise continuity for this quantity, but I have pointwise continuity for the integrated quantity. Right? So now I get the chain rule, the side chain rule, even at the level of gradients in some sense. Okay, and this concludes the proof. All right. Okay, good time to take a few minutes break.
Sorry, can you explain the last step again? This was too fast.
Sure. Are you up to here with phi affine?
Yes. Yeah. So,
Okay.
so phi affine, piecewise affine. Okay, and then you do what?
So then what I know is that for every phi piecewise affine, I know that this. Let me write it this way: phi n composition f you agree? For every sequence phi n of piecewise affine. Now, if we pick phi n converging to our phi in the same way that we got it before, we get that phi n composition f will converge in W12 to phi composition f. Right? Because they converge in L2, and the minimal weak aggregate of the difference is equal, or if you want, well, actually is equal to phi prime minus phi n prime composition f minimum weak aggregate of f. Right? And this expression goes to 0 in L2. That's my claim, if you want. And this goes to 0 in L2 because minimal weak aggregate of f is in L2. These functions are uniformly bounded because phi and the phi n's are uniformly Lipschitz. Okay. And then there is this issue of points of non-differentiability that can be handled as before. So in any case, in the preimage of any countable set, this minimum weak aggregate is 0. So this causes no problem. So this, if you want, this function is converging to 0 pointwise almost everywhere. Let's put it this way. All right.
And then you want to use like Cauchy-Schwarz or something?
No, no, now I want to use the continuity that I proved before. So now, given that phi n composition F goes to phi composition F in W12,
Oh,
this,
you want to use, okay, got it.
this by continuity, yeah, I cannot use Cauchy-Schwarz because I don't have linearity in the gradient, but I can use this trick. The continuity is still there. And of course, on the right hand side, things are just simpler, right? Because I mean, the gradient of F never appears.
Okay, got it. Thank you.
Okay. No, sure. I mean, say yeah, sometimes I go maybe a bit too fast. I mean, that's okay. All right, I guess we can start again. So now I want to use this newfound technology, if you wish, of integration by parts and the alike. And I want to use it in order to better understand the properties of the heat flow. Okay. In particular, it should be clear now that infinitesimal Hilbertianity is linked to linearity of the heat flow. And so the next question is, okay, if I have a CD infinity space and I know that the heat flow is linear, what else can I say? I mean, I should have now a very Riemannian-like situation, and I want to have a Riemannian-like property then. And okay, so the path from now to the end of the series of lectures is, well, on one side, we will continue to develop calculus tools. And on the other side, we want to use these calculus tools to better understand both the analysis and the geometry, actually the geometry of the underlying space. Okay. Now this won't be quick. Okay. Still more work is needed, and so I mean let's continue. And one thing, actually, perhaps let me point out the following. I mentioned the first order differentiation formula, or if you want, these horizontal and vertical derivatives. That is something that has to do with plans representing gradients. Right? You remember, if pi represents the gradient of f, then whenever I differentiate g direction pi, I know what the result is. I still have not given you any statement concerning existence of such plans representing gradients, and I will do now. And that's basically the only case where we will use this concept of plans representing gradients. And here is the theorem, if you want. If you want, this is a metric version of Brenier-Mecan theorem. This has been proved by Ambrosio Savary and myself. And the same goes as follows. Let me cheat. Let me say X compact. It's a terrible assumption. It's totally unneeded, but it will save my life or my time at least. So say that X is compact. Let mu0, mu1, two given measures, and let's say that n pi, actually, let me put it this way, and mu t a W2 geodesic, connecting them, from mu0 to mu1. Now, and let phi be a Kantorovich potential. So it maximizes the dual program. And also, and let pi, this is a probability measure on this space, of fast on X, be a lifting of mu t. Assume, okay, so far I basically made no assumptions on the space, on the metric measure space XDM. Here is the crucial assumption, which is a very heavy assumption. You will not have this assumption on arbitrary metric measure space, but assume that the density of mu t is bounded by some constant times m for every t. There exists C such that. Okay. So for some reason, these measures along the geodesic, they all have bounded density. Okay. Notice that, of course, this assumption speaks about the relation between the reference measure M and at least this Wasserstein geodesic. Okay. Well, then pi represents the gradient, gradient of minus phi. Okay. I'll prove this in a second. Actually, the proof is surprisingly simple. But I want to comment on the statement first. So what it is that Brenier-McCann theorem tells? So suppose X was a Riemannian manifold, and this was a geodesic of measures made of whatever smooth densities you want. Well, then pi. Well, now in the smooth notice, remark. In the smooth case, we knew that pi would be the push forward. Let me put it this way: the push forward of mu 0 via the map that takes where f is the map, the curve that takes t and returns ft of x. This is nothing but the exponential map with base x of minus t grad phi at x. So that's what McCann tells. Okay, tells you that if phi is a Kantorovich potential and everything is sufficiently smooth, then you are going from mu 0 to mu 1 following this map. So you're sitting at x. Where do you shoot x? Well, you shoot x in the direction of minus grad phi. So f at times t is exactly x with base x of minus t grad phi at x. Minus t times grad phi x. Okay. So in particular, the derivative at time t equals 0 of this curve, f prime at time is 0 at x, this is equal to minus grad phi at x. Right? That's a corollary, a very partial information with respect to what McCann tells, but this is true. And this is what this is telling. Okay. In fact, something more could be said. In fact, one could also say, and I could also say that the distance between gamma 0 and gamma 1 is equal to the minimal weak upper gate of phi at gamma 0 for pi almost every gamma. That's also something I will come with the proof. So McCann and Brenier, they also tell you, knowing the base point, they know where you are sending the, this point. As I mentioned, you're sending it to exp minus grad phi. So they know exactly where you're sending it. Now here, you don't know exactly where you're sending it. The conclusion is not that pi is induced by a map. I don't know that. But I know at least that the distance that every point travels depends only on the base point. Okay. And there's a good reason why I don't know more than this. because say in R2 with the L infinity norm, or on any Banach, space with not a strictly convex norm, you can find examples of, geodesic as above, where you don't have optimal map, but you just have optimal plans, and but the distance where the distance at this track. Okay. All right. If I don't know if you. So how many of you have experience with the L1 optimal transportation with cost equal distance? I don't know if you. So if you have experience with that, you might have heard that in L1 optimal transportation, you not only have maps but also plans, because the optimality in the dual problem tells you only the direction where you're moving, but not how far you're moving. Okay, this is the dual situation. My cost is distance squared, but maybe my distance is not strictly convex. So I know how far I'm moving, but maybe not the direction. Okay, so that's okay. Anyway, proof. So what I know, what does it mean that phi is a Kantorovich potential, and that pi is a lifting of mu t? So I know that E0, E1 push 4 pi. This is an optimal map, optimal plan. Right? Should I prove this? Maybe I should, right? So why is this true? So what is the integral? Let me copy this. What is the integral of gamma t dot square dt d pi of gamma? What is the kinetic energy of this plan? Well, this is certainly greater or equal than the integral of distance squared gamma 0, gamma 1, right? D pi of gamma. Just because the distance between 2 points, the energy bounds the distance. Okay. On the other hand, given that pi is a lifting of this measure of this curve mu t, this is equal to the integral from 0 to 1 of mu t dot squared dt, by the definition of lifting. Okay. But mu t was a geodesic, and geodesics have constant speed, and speed equal to the distance between their endpoints. So this is equal to W2 squared mu 0 mu 1. Right? So the cost of this plan, which is this quantity, is less or equal than the square distance. And therefore it's equal. It cannot be strictly smaller. So this claim is proved. Now this is optimal. Pi is a Kantorovich potential. Therefore, what I know is that by the fundamental theorem of optimal transport, is 0 and 1 push 4 pi. So this is concentrated on the SISSA per differential of phi. Right? So for pi, in other words, for pi almost every gamma, I know that the following is true. Well, I know that phi at gamma 0 is equal to phi c, actually minus phi c at gamma 1, with this plus distance squared gamma 0 gamma 1 over 2. Let's say that cost is distance squared over 2. If you otherwise, I mean, you have to decide what c is. For me, c is distance squared over 2. The proof changes nothing if you just a matter of paying attention to it. Okay. So okay, now on the other hand, of course I know that phi at any other point, say for instance gamma t, is less or equal than phi c at gamma 1 plus distance squared at gamma t gamma 1 divided by 2. Right? Just by the duality formula. Right? Phi is c concave. So phi is the inf of it's okay. Right? So phi, I'm saying that phi is equal to phi cc. Right? So because of this, phi at any x is less or equal, actually is equal if you want to the inf over y of minus phi c of y plus distance squared xy. So just okay. Well, but then the difference between these two, phi at gamma 0 minus phi at gamma t, this is greater or equal than, okay, what is that I have? I have distance squared gamma 0, gamma 1 multiplied by what? By 1/2 minus 1 minus t squared over 2. Gamma is a geodesic. So the distance between gamma t and gamma 1, I know what it is 1 minus t, this distance, right? The distance goes linear. So this is something that I can compute. Okay, but what it is this? I will make confusion. Well, I mean, this is something that we should be able to compute. And this will give us, in particular, let me write here the conclusion. The conclusion is that the limit of the integral of phi gamma 0 minus phi gamma t divided by t in the pi, this is greater or equal than the integral of distance squared. Actually, yeah. So this is greater or equal than w2 squared mu 0 mu 1. Right? Because no, when you expand the squares, so this is 1/2 minus 1/2 minus t squared over 2, and then I have plus t. Right? So this simplifies. I divide by t. I integrate, right? And then this t squared divided by t, I still have a t which disappears in the limit. And what I get when I take the limit is just that this limit is greater or equal than the integral of distance squared, the pi, which is, as we mentioned, is w2 squared. Okay, so this is one inequality. Another inequality is all right. Oh yes, it's even simpler. So on the other hand, I know that yeah, I know that phi of y for this very same reason over here, phi of x, let me write it. Phi of x minus phi at gamma 0. For this reason, so this is less or equal. I use y equal gamma 1 in this to bound from above this quantity. While for y equal gamma 1, I have this equality over here. Okay, so this is less or equal than, and as before, phi c drops, and what I get is distance squared x gamma 1 divided by 2 minus distance squared gamma 0 gamma 1 divided by 2. Okay, well then this is less or equal. This is the diff. So 1/2. Well, actually, distance x gamma 1 minus distance gamma 0 gamma 1 times the sum of the two divided by 2. Distance x gamma 1 plus distance gamma 0 gamma 1. Okay, but now this is, of course, triangle inequality. This is bounded from above by the distance between x and gamma 0, and then I have times this quantity. Right. So if you divide by this quantity and you let x go to gamma 0, what you get is that the lim sup. Let me give a name. Well, this lim sup as x goes to gamma 0 of phi of x minus phi of gamma 0 divided by the distance between x and gamma 0. This, let me take also the positive part. This I will call it, the upper slope of phi, or actually this slope. Let me see, at gamma 0. This quantity is less or equal than the distance between gamma 0 and gamma 1. Agree? Because when x goes to gamma 0, the distance between x and gamma 1 will converge to the distance between gamma 0 and gamma 1, so I have twice the same quantity, and I get this. Okay. Okay, now it's time for a remark. Please. If f is Lipschitz, we are on a compass space. If f is Lipschitz, then the minimal weak upper gate of f is less or equal than this sort of slope almost everywhere. what we know if you want to read is that the minimal weak upper gradient, the sober quantity, is less or equal than the asymptotic ellipsis constant. Okay, that comes from the relaxation point of view. Okay, now I want to say that it's less or equal than something potentially quite smaller than the asymptotic ellipsis constant, because I'm only taking, in some sense, a one-sided variation, and I'm also fixing, one of the 2 points. Okay. Now, why is this true? Well, this is true. I can prove this by using the weak upper gradient property. The point is that if f is Lipschitz and gamma, notice that if gamma is absolutely continuous, then I still know that t, I mean, this I already used, f gamma t is absolutely continuous, right? And what I claim is that the derivative, this derivative, is bounded from above, is less or equal than the upper slope of f, if you want, at gamma t by times gamma t dot for almost everything. And why is this true? Well, I guess for trivial reasons. Actually, is in modulus. Okay. But this is just because an absolute continuous function, on the real line, this is almost everywhere differentiable. Take a point of differentiability. Take t differentiability point of this one, f gamma t. Right. Now, if the derivative is positive, if the derivative is positive, well, then this derivative, what it is? This guy is is the lim as h goes to 0 of f gamma t plus h minus f gamma t divided by h, right? But if the derivative is positive, I can also put, right? And this is this is bounded from above by this slope. Then you divide. Then you divide distance gamma t plus h, gamma t distance divided by h, and you're done, right? What if the derivative is negative? Well, if the derivative is negative, you do the same, except that you write that this derivative is equal to the limit when h goes to 0 from below, right? Of the same expression. Right? But when you take the absolute value of this thing, you are so then the modulus of the derivative is equal to this, right? And then again you take the positive part and you're done. Okay. So this proves my claim, right? Because I proved, that this upper slope for Lipschitz functions, this upper slope is in fact an upper gradient. So that's the job of the upper gradient along any absolutely continuous curve. And since clearly this upper slope is bounded by the global Lipschitz constant, my space is compact, so it has finite measure. This global Lipschitz constant is in L2, is in whatever LP. So this is in fact a weak upper gradient, because it's way more than a weak upper gradient. So our minimal weak upper gradient is smaller than. Okay. So let me write what it is that we proved here. So we proved that the minimal weak upper gradient of phi in gamma 0, this is less or equal than the distance between gamma 0 and gamma 1 for pi almost every gamma. End of the proof. Right? We have 3 things. We prove 3 things. We prove this, we prove this, and we prove this. Right? So let me just make, take this all together. So this limit, this is what we want to control if I want to prove my claim about plan representing gradients. This guy is greater or equal than W2 squared. But this is greater or equal, actually, well, this is greater or equal than, let me put it this way. So I have 1/2 W2 squared plus this quantity over here, which is 1/2 the limit as t goes to 0 because in fact for every, so this quantity is constant in t, so I'm writing limit t as a very complicated way, but this is a constant quantity because of this, right? If you want the energy, the kinetic energy for any s, for almost every s, this kinetic energy is equal to the squared speed of the curve, but the squared speed of the curve is always constantly equal to the square distance between the endpoints. So if I'm taking the average or not, doesn't matter. And now this quantity, this is equal to the 1/2 if you want into this squared gamma 0 gamma 1 d pi. But now I use this, and then I get that this is greater or equal than 1/2 the integral of the minimum weak coupling of phi squared gamma 0 d pi plus 1/2 this lim sup, which is what is required by plans representing gradients. Given that here there is a phi at gamma 0 minus phi at gamma t represents the gradient of minus phi. Okay. If you want, is minus phi at gamma t minus phi at gamma 0. Okay. And what about this last statement? Well, this inequality cannot be strict, right? Because in plan representing gradients, no inequality can be strict. So if this inequality cannot be strict, it means that this inequality must be an equality for pi almost every gamma, which is precisely what. All right. Okay. Yeah, I guess in our paper you will not find this statement written in this way, but that's basically what we proved. This statement is there, but anyway, yeah, I'm restating a theorem. I mentioned this because maybe you look for precisely the same statement, but you won't find it there. Okay.
Sorry, question.
Please.
Where did you use that mu t was less than some constant times m?
Say it again, sorry.
Where did you use that mu t is less than or equal than c times m?
Oh, you're right. What did I use? Good question. What did I use? On the fact that pi, in order for pi, good point. Never, I guess, except in here. So in order to say, thank you. In order to say that pi represents something, pi should be a test plan. And in order for pi to be a test plan, its margin should be uniformly bounded.
Oh, okay. That's
okay. There is also another point. Thanks. I should have clarified this. So, at least I use the fact that mu0 is absolutely continuous. Namely, when I integrate the minimal weak coupling of phi, composed at gamma 0 in d pi. Thank you, Vitali, for this question. So if I write this integral, I should be sure that this integral is well defined, right? And the minimal weak coupling gradient is only defined m almost everywhere. So if I know nothing about E0 push over pi, I cannot write this. You see what I mean? So if I have, so I guess this is a general fact. So if I have a function f well defined, mu almost everywhere, and I want to, and I want to, compute f composition T, and I ask whether this is well defined. In order for this to be well defined, nu almost everywhere, I should be sure that T push over nu is absolutely continuous with respect to mu. Huh? Make sense this? Right? Because if I have a set of positive nu measure that is sent in a negligible set of mu, then I have a problem defining this. Huh? Make sense? So I'm using here, in order to write this, thanks Vitaly, I should have been more explicit. In order to write this, I should have, I must be sure that E0 push over pi is absolutely continuous with respect to m, which is where this function is defined. And of course it is, because pi is a lifting of our family of measures, and in particular, you have a question?
Yeah. But if you are on a Riemannian manifold,
Yes.
just assume that mu0 is absolutely continuous with the volume measure. This gives you that mu t is absolutely continuous for short time.
Yes, in fact, for every time up to strictly less than 1. Yes.
So in general, if you have
Not 1, of course, because
if
you can get to delta. Yes, of course.
When do you have like a Lipschitz map? Because I guess that the reason why this inequality holds is that the exponential map is sort of Lipschitz.
Haha, no.
No,
It's because of Ricci curvature. No,
okay.
no, I can't do that. No, the optimal map, the optimal map is never Lipschitz. Never Lipschitz. Okay, never. It's an hard time to prove that the optimal plan is induced by a map. So getting that the map is continuous would be another regularity, and then Lipschitz another regularity, forget. Okay. You get that sort of statement whenever if you have a geodesic and you sit at the interpolate, say the midpoint measure, and you look at the optimal map from that midpoint measure to the initial and finite measures, then in the Riemannian setting, this would be a local Lipschitz map. But they're for totally different reasons in some sense. No, that has to do so okay, now it comes. I mean, I was going exactly in that direction. Let me present the result in the metric setting without proof. I will not prove this. This is too long to prove. This is a proposition. That's a useful, an extremely useful proposition by Rayala, Tapio, around 2011. And the statement is this: let X be a CD K infinity space, and again compact. Absolutely not needed, but let me say compact. Let also mu0 and mu1 be probability measures on X that are, bounded from above by some constant. Okay. Now we have two measures bounded by a constant and the space which is CDK infinity. Well, then what Rayala tells is that then there exists a W2 geodesic from mu0 to mu1, such that two things are true. First of all, the convexity inequality holds. So in particular, the entropy of mu t is less or equal to the same inequality that comes with the definition of CDK infinity space. What this is minus k over 2 t minus 1 minus t w2 squared. And second, I mean, this is lost convenience by definition. So Rayala tells you something more. Second is that you can choose such geodesics so that this holds true for every t for some C prime. Okay. So let me comment. So first of all, if you follow Rayala's proof, now I'm being a little bit dishonest in here. So he tells you exactly who is this C prime in terms of the statement. And that C prime is the same C prime that you would get on a Riemannian manifold. On a Riemannian manifold, if you pick the only geodesic, and Kant tells you that there is only one, connecting two measures with bounded density on a space, on a manifold which is compact, and there's some unit. So in particular, you have a control on how far these densities are, and you have a lower bound on the Ricci. Then you get an upper bound on the intermediate density, and Rayala tells you exactly the sharp upper bound. Okay. So first thing. Second thing, and perhaps I want to make another comment in the direction of what you were saying, Luca. So I think you had an inequality in your mind which was going in the wrong direction. In some sense, what you want from the optimal map in order for this to be true is that the optimal map does not shrink stuff too much. No? If the optimal map is the most regular map, the constant map, no? Then T push forward, constant push forward any measure is a direct mass. So this typically tends to be not true. What you want is that the mass remains spread out, probably, which is exactly this spreading out is exactly what should come with loss turbulency. Okay. Now this theorem would be trivial if we knew that that we had a geodesic whose lifting is concentrated on geodesics that do not intersect. So rough idea, very rough idea, very rough idea. At least as to why this could be true. Very rough idea, or perhaps it's a comment in this. So let pi be the lifting of the Loth-Trubill-Lani geodesic, meaning the one that exists because of the Loth-Trubill-Lani condition, CD K infinity condition. And let's assume, and let's pretend such that for every T in 0, 1, let's say at least intermediate, the map that takes gamma and returns gamma T is pi injective, is pi essentially injective. Pi essentially injective. So what does it mean? It means that pi is concentrated. Let me say it like this. So actually, let me say it like this so that I don't have to introduce. So let me such that there exists gamma set of curves, Borel, and such that pi of gamma is 1. So pi is concentrated on this set of gamma. And such that ET restricted to gamma is injective. So this means that whenever I have a certain initial distribution, I find a distribution, I have this plan that is the lifting of the geodesic, and for some reason I'm so lucky that these geodesics, whenever I look at them in time t, I always find different points. Okay, so this means that if I want to look at the density of ET Peugeot gamma at some point, in some sense that density only comes from this geodesic. Okay, and let me also pretend, assume also, this is absolutely in general absolutely not true, but assume also that for every A in Borel here, Borel with pi of A positive. If I look at the the curve, if you want, if I take my plan, I restrict it to A and then I normalize, this guy, and then I look at his marginals. This is also a lost room with an isodisk. What am I saying? I'm saying, look, this plan, this plan is such that whenever I look at its marginal satisfy the inequality in one. Okay. I'm saying, look, pick some geodesics, take a bunch of these geodesics of positive measure, forget about all the others, and rescale the restrict and rescale the plan. Okay. Now you have another plan living on the space of geodesics. This is an optimal plan between its marginals because the support of this plan, the new plan, is contained in the old support. And assume that the entropy is still convex along these geodesics. Okay. Well, if you have all of this, it's not hard to check. If you have all of this, it's not hard to check that it is not hard to check that not only you have that convexity that I brought in one, but you have the better convexity, which is a log of rho. So call let rho t m. This is et push over pi. Then log rho t in gamma t is actually less or equal than 1 minus t log rho 0 in gamma 0 plus t times log rho 1 in gamma 1 minus k over 2 t 1 minus t distance squared gamma 0 gamma 1 for pi almost every gamma. Let me comment 1 second on this inequality. First of all, it should be clear that this inequality is the pointwise version of 1. If you have this and you integrate with respect to pi, you get exactly, if you integrate here with respect to pi, let's look, for instance, on the left-hand side, integral of log, what is this? Log rho t in gamma t d pi of gamma. What it is this? This is equal to the integral of log of rho t d et push over pi, et push over pi. But et push over pi is rho t m. Right? So this is equal to the entropy of et push over pi. Make sense? Right? And the same for rho 0 and rho 1, because here there is gamma 0, gamma 1. And if I integrate distance squared, the pi is optimal, I get W2 squared. Okay? So this is the pointwise version of 1. And therefore, it's of course stronger. I mean, if you have this and you integrate, you get 1. But of course, a priori, 1 does not imply this pointwise version. In order to get from 1 to this pointwise version, I had to assume basically, that whenever I restrict my plan, I still remain a plan that satisfies the CDK assumption. Okay? Now, say that you have a plan that satisfies this, an optimal plan that satisfies this. Well, then you see, you can use this inequality to get a bound from above on the log of rho t, and therefore on rho t. Right? Because so rho 0 and rho 1 were bounded from above by some constant. Right? So this quantity and this quantity are uniformly bounded in gamma, in t, in whatever. Okay. Now, this quantity k over 2 t times 1 minus t distance squared, this is also bounded from above by some constant. If k is positive, you can just drop this term. If k is negative, well, then pick the absolute value of k, and here you put the diameter of the space, and still this is uniformly bounded. Okay. So in any case, if you have a plan pi for which this is true, well, then you have found, an upper bound on the density of rho t, which is exactly what you want. Right? Okay. Now, perhaps here is a good point to make a comment. So, first of all, in the Riemannian setting, when you prove this Sturm-Voronezh theorem that a lower bound on the Ricci curvature implies convexity of the entropy, what you prove is actually is this inequality. And then you integrate this inequality and you get the complexity. Okay. So now, of course, you can wonder, well, but if this is the useful inequality, or in any case, if this is stronger than that, why didn't Loss-Villani use this inequality to define this infinite space? And the answer is, of course, in the stability problem. This, if you start from this, you don't know whether, this is not stable under weak convergence of geodesics. You don't know that. Okay, so you cannot use that. Okay. So the lower Ricci bound, and here comes, the final comment in your question. So the lower Ricci bound really what tells you is this inequality over here. So the density at the intermediate times is bounded from O by, density in a very quantified way, the density initial finite time. And this gives in particular gives the bound of interest in this case. Okay. Now, what did Rajala do? Rajala, okay, so he knew that he could not get, exactly this. And there are several difficulties that occur in handling this. One of those is that this very first assumption might be not true. What could be true in general, if you start, from a density here, a density there, is that your plan does something like this. I don't know. And there are many geodesics that pass on the same, actually, really on the same point. See, I don't know there. They are still sufficiently spread out that the entropy is convex, but there is a little bit of overlapping. And if there is a little bit of overlapping, it means that the density, say at rho 1/2 at this point, comes from the density from several densities at the start and final point. So you cannot hope for an inequality so smooth, in such sense, so nice to be true. Okay, so that's one of the problems. And the other problem, of course, is that okay, you have just the integrated inequality. You have no idea. You have no idea whether you can localize. Which, okay, it's a quite. It's the same sort of conceptual problem that is in the idea. So the idea, but then this requires some computations. I will not show you the computation. Once you get the idea and the good understanding optimal transport, this computation, at least the advantage, they're easy to follow. Hard to find, to be honest, but if you pick Rajala's paper and you sit down, it's a couple of pages, and you sit down quietly and you read them in say an afternoon, you should be able to come out. I have no idea how he managed to get that, because it's sort of miraculous, but at least the paper is well written and nice to read. So the point is this: what he says is that actually it tells you exactly who is the geodesic, and the geodesic is made like this: take mu0, take mu1. First of all, you don't know whether there is only one geodesic or many. Loss-Villani don't tell you anything about this. So in particular, you can have many midpoints. Okay? Well, you pick among all the midpoints, you pick the one which minimizes the entropy. By convexity and lower semi-continuity, there should be such one. Okay. So you start, you have your mu0, mu1, you have your entropies, you have many midpoints, and you pick the one that minimizes the entropy. And then you pick the one that minimizes, 1/4 you minimize the entropy over here, 3/4 you minimize the entropy over here, and you continue like this. And now you build, in a sense, a dyadic geodesic. And if you want by lower semi-continuity, then you get, you can extend this to a geodesic, and by lower semi-continuity and optimality of these midpoints that you previously chosen, you know that you have this convexity of the entropy satisfied. So one holds for free. And then what it does is, okay, let's suppose that for some reason this is not true for this C prime that comes in some sense from the Riemannian analogy. Well, then what I do is I remove, say that in this region the density was too high. Well, then what I do, I pick my optimal plan pi, I take out all of these geodesics. Okay. Given that I took out all the geodesics, now the initial and final mass will not be anymore my rho 0 or 1. So I look at the initial and final distributions of the set of geodesics that I took out. And for that, I apply the Loss-Villani. I pick the Loss-Villani geodesic. In some sense, that this geodesic that I chose still had, an initial and final bound. They still had, because rho 0 and rho 1, the final density. But they were, instead of concentrating a lot to create a density higher than C or C prime. Well, Loss-Villani give me another way of interpolating between them in order that the entropy stays low, because if the density is high, the entropy is high. But I want, if the density is uniformly high, the entropy must be high for sure. But give me another, another plan. And if I use this new plan and together with what I had previously, basically I have something with less entropy in that point where there was concentration. I mean, this is roughly the idea. Okay, I understand it's very rough. I don't pretend you to, get the point, but at least, maybe some more. I mean, if you ever want to read Ayala's paper, these words that I mentioned maybe can help you guiding your intuition. Anyway, just to close. So what we will do, I will not prove Ayala, but I will use Ayala as a black box. So I apply Ayala's theorem to the metric Riemannian theorem. So on CD and 3D spaces, we will have many test plans, coming from vast and geodesic that represents gradient of control potential. Okay, and on Friday we will use this to get what is called the EVI property of the gradient flow, of the heat flow. Okay, we'll get contractivity in vastest time for the heat flow. Okay, so that's all. If there are no questions, see you on Friday. All right.